Hey, everybody. Hey, Jadelle, cute hat.
Thank you.
Ainsley and Matt, hello. Hi, Gabrielle, Daphne, Sophia. Hi, Kevin, James, Kelly, Ian, hello. Hello, Matt, Giovanni, Thomas, Will. Do you go by William or Will?
I go by Will.
Oh, Will Lyons does. What about William Hanna?
Either.
Either, okay. I should have asked you like 3 months ago, right? Sorry. Hey, Zach is here. Connor's here. Drew is here. I don't see Tom, Dylan, or Will. Can you guys put your video on, please? Thank you. Will is in transit somewhere. Joey and Grady, are you guys with me? Thank you, Grady. And one last person, Dylan. Dylan, are you there? Your microphone's off if you're trying to talk. Yeah, no problem, Jadelle. All right, Dylan might be having technical difficulties. All right, how's everybody doing? How was your weekend? I'm almost done grading the extra credit assignment, so that hopefully I will get that in today. They were interesting. Took a little longer to read them than I thought. So you guys did a great job. All right. So let's talk logistics. Today we're going to review for the chapter 4 and 5 test. And let me share my screen. I got to get you guys back now. There we go. Okay, so today we're going to review for the chapter 4 and 5 test, and then on Wednesday we will have that test, and I really need everybody to take it on Wednesday. I got a time crunch, okay? So if for some reason you're thinking you can't take it, I need to hear from you right away, and we're going to set up a separate time. But I would really appreciate it if everybody could take it on Wednesday. It's one of the sections that's you can use Desmos for so many of the questions, right? You just need a general understanding. It's not a particularly hard section at all. You'll see from this review, because one of the sections that is harder, we ended up eliminating altogether because of time. So it's not on the test, and it won't be on the final exam. That I think is 4.6 that we eliminated. All right, so Wednesday we're taking the test, and then the following Monday we will be reviewing for the final exam, and your final exam is not until a week later, or I think 10 or 12 days later. So check when you guys check online, because the pacing guide is updated. So you shouldn't really email me to ask me what's going on the next class period, because it's all posted for you. All right, anybody have any questions for me before we begin?
Yes, I have one question. I don't know if you said this already, but have you graded the extra credit yet?
Yeah, when you were gone, I said that I'm about halfway through. I should have it done by today.
Sorry, thank you.
Yeah, if you did, as far as I know, and I've read half of them, if you did it, you're going to get some extra credit. Okay. Okay, so I did update these notes recently. I think maybe like if you didn't print it out before noon, you should have the one that said updated, then you're good. So there's a lot of examples that I have done here, but I'm trying to write a lot of it down for you, so you're not watching me write instead of watching we do problems. So some of the stuff that I would have written next to this figure is just so that you know what are the points called. Oops. Lost my tip. There it is. There we go. Okay. So a couple of buzzwords, inflection point. Notice that the inflection point is, oh, I should use blue. They're using blue. So inflection point is where the original f of x function will change concavity, right? Notice that it's concave down here and then it goes to concave up. So that's where your inflection point is. In this particular graph, if a graph goes off, really these arrows are implied. So it doesn't have an absolute or what we call a global max or min on this graph because this is going down forever and this is going up, right? So no global max or min, but we do have a local max. Is this a color? No, it's not here. We do have a local max and a local min, right? So here they're just saying max, but this is really called a local max, and this is your local min. So if the slope of the lines change from positive to negative, it's going to be concave down, right? So, and this is what I mean by that, because this diagram doesn't really do it well. But see, here they're saying the slope is positive. So it's slope meaning at individual points, right? So if you did the derivative of individual points on the original graph, the slope would change from going positive in that direction to negative in this direction. So that's how you know that it's going to be concave down. And the same idea if it's concave up, right? It changes from being negative, right? Here it's negative where I just drew those lines and goes to positive. So it's kind of, intuitive too, obviously. Okay. So here's your first example. It says to find all critical points. And on a test, I'm not going to put what's in parentheses. I just didn't want you to spend too much time writing, right? I wanted us to spend more time doing problems. So to find the critical points, that's the x value where the first derivative will equal 0. So
I have a quick question.
yeah,
Will this be on Wiley for the people that are home, or is it like the first test?
no, everybody's taking it on Wiley. Yeah, I'm not in Baltimore anymore. I'm in Florida. Okay, so to do the derivative of a quotient, we have to use the quotient rule. And just to remind you, the quotient rule says to take the derivative of a quotient, you're going to use this formula. Oops, sorry, that should be minus. That's the quotient rule. All right, so let's identify. So we've got our f here, the numerator, and our g is the denominator. All right, so we have f prime, which is 1, right? Because x to the first power, so it's 1 times g, which is just x squared plus 1, minus f, which is just x, times g prime, which would be 2x. And then your g squared would just be x squared plus 1 quantity squared. All right, now if you simplify that, you'll get, if you simplify and distribute the numerator completely, then you're going to get just 1 minus x squared over x squared plus 1 quantity squared. So that's just a simplified version of it, okay? And then since we're going to set it equal to 0 in order to find the critical points, let's do that now. Now, rational expressions are easy to solve because, especially when you have them set to 0, because if you multiply both sides by the denominator, it completely goes away, right? So you're just left with 1 minus x squared is equal to 0. And then from there, you're just going to factor this using difference of squares pattern. Difference of squares says that if you can write something like a squared minus b squared, then you can factor it like, whoops, and you can factor it like a plus b times, I was going to say x again, a minus b. So if you factored this, you could get 1 plus x times 1 minus x. And then if you solve each of those for 0, right, 1 plus x is how you're going to get your critical points. Okay, so the critical points are the x values when you solve for x and you set the first derivative equal to 0. So that's the first step in a lot of this chapter 4 stuff, is finding the critical points. Now we're going to use the first derivative test to determine local max and minimum. Now there's a couple of different ways that you can figure out where max and min is. This is specifically asking you to use the first derivative test. And that's all this stuff. So let me show you what I'm going to do first, and then we'll answer that. Okay, so we know that our critical points are -1 and +1. So let's see, what's find -1? Be somewhere there, right? Critical points. So we're going to say, okay, well, what does the graph do when x is less than 1? What does the graph do when x is between -1 and +1? And finally, what does x do when x is greater than 1? In the original function, or sorry, in the derivative. So if we take f prime of a number less than -1, say -2, we put that in the derivative formula, and that's this formula up here in black. Okay, so everywhere we see x, we're going to put -2. You get a number that is, and what the number is isn't important, but we get a negative number. So we get a number less than 0. What that means is that in that interval, x is less than -1, we can say that the graph is decreasing. Since you evaluated it for a number in that interval and it's less, and the derivative is less than 0. If you did the same thing for a value between -1 and +1, say 0, you'd end up getting a number, and we don't care what number it is, we just want to know if it's greater than or less than 0. So it's greater than 0, and that tells us that the graph must be increasing. And the same thing, let's pick a number that's greater than 1 and evaluate the derivative, say 2. If you do that, you get a number that is less than 0, which means that it's decreasing. Which you can clearly show. Remember at the beginning of this lesson today, I said you can use so much graphs to answer the same questions that I'm doing through theory, right? So if you're stuck on something, graph it in Desmos. Okay, and I'm going to keep trying to reiterate that. All right, so here's one critical point at -1. Here's another critical point at +1. So since it goes from decreasing to increasing, right? Then we can say, actually, let me use a different color for this. I'm point out the difference. Here it's going from decreasing to increasing. here it says, if it's greater than 0, then F is increasing, right? We know that, and that's how I'm getting all of this data right here. And if it's less than 0, then it's decreasing, whatever. And if it's 0, then it's just constant. Straight line. Okay, so now we're going to determine local max and local min. Well, if a function, right, remember, this is saying that f of x is decreasing, right? If a function is decreasing and then increasing, this is going to be a local min. Right? Because you can kind of follow the graph. So at -1, we're going to have the smallest part of the original graph. Then if we go continuing on here, so here we're going from increasing to decreasing, right? It makes sense that it would follow this curve. It increases and then it decreases, right? So here you have a local max. So that's sort of intuitive, but look at the graph. It's right here. I just used Desmos. And in Desmos, you can click on it and it'll give you the point, right? Okay, what else is it asking us to do? So we've determined that -1 is going to be a local min. And look, it makes sense, right? Because this is the lowest part of the graph. And the local max is here at +1, which makes sense if you look at the graph as well, right? You would probably answer that question without doing this. Okay, so use first derivative to determine local max and min. So what we determined is that the local max occurs when, local min when x is equal to -1. So if we find out, well, what is the point at -1? This is when they ask you to evaluate it at its critical point, right? The critical points are just the x values. But if they say, well, where is that on the graph, or evaluate at the critical points, right? You could say, well, f of -1, if you put that in, you're going to get, well, let me just show you. -1 squared plus 1. I'm just putting it in the original question. And you would get -1/4. If you did f of +1, you'd get +1/4. And look where it is on the graph, right here and here. And look at the scale is bigger, right? So this is 1. So you could say that this point is -1, -1/4, and this point over here, the min, and the maximum would be +1, 1/4. And then it says check your answer by graphing. If it ever says that, guys, graph it on Desmos first. Question, Zach?
Yeah, could you scroll up to where you wrote in red? You see how the denominator is like squared?
Yes.
So wouldn't there still be a x squared plus 1 in the denominator?
Well, what I'm doing is, no, because what happened, I'm glad you asked that question, Zach. Great question. If I do something to both sides of the equation, it's totally legal, right? As long as I do the same thing to both sides. So the reason why I'm multiplying by x squared plus 1 is to get rid of the numerator and the denominator, right? Because anything over itself is just going to equal 1. So that's why all I'm left with, Zach, is the numerator, because the denominator's canceled out.
Yeah, I just like, I don't know. I thought you would have to multiply it like squared too. Like,
Oh, you mean up here? Yeah, actually, you're right. Actually, you're right. Yeah, sorry. But as you see, it cancels out, and anything times 0 is just 0. So either way, you're just left with the numerator. But I'm very glad you brought that up, because that might have confused somebody else too. Thank you. Any other questions while we're here? Sweet. Okay. I guess I was just saying the denominators cancel out or whatever, but you're right, I should be more precise. Okay, so up here, we use the first derivative test to determine where the local min and max are. Here, we're going to figure out what the local min or max is by using the second derivative test. The second derivative test says that if you put a number in and it's 0, and the second derivative, in other words, you have a critical point, and the second derivative at that critical point is negative, then it's concave down, which means it has to be a local max, right? And here, if you put a critical point in, or you have a critical point and you put that into the second derivative and it's greater than 0, then you necessarily will have concave up, which means that you would have a local min. So, all right, let's see what this shows us. Anybody can answer, where's the critical point? Here, they're not giving us a function, right? They're not giving us a formula or whatever. They're just giving us points on the graph. What's the critical point based on the fact that those three things exist? So this is just a plain old point on the graph, right? This is the first derivative. Whoops, let me get a different color. This is the first derivative at that point, -5. So you put a -5 in to the derivative and you get a 0 out. And then this, oops, is what we're going to use for the second derivative test. Here. So where's the critical point? Where's the derivative equal to 0? Anybody?
First derivative.
Where is the first derivative equal to 0? What x value makes the first derivative equal to 0?
-5.
Yeah, absolutely. -5, right? It's right there. So you could say first derivative equal to 0. So if they ask you for the critical point, you know that the critical point occurs or is when x is equal to -5, since first derivative equals 0. All right, now we're going to use the second derivative information. So we can say the graph is concave up Why can I say the graph is concave up according to those rules? Well, if I put this critical point inside the second derivative and it is positive, meaning f of the critical point is greater than 0, right? It tells us right there in yellow that if you put the critical point in, you're going to get a positive number. And according to this, it says that if the second derivative at the critical point is positive, then it's concave up. So it's concave up because second derivative at -5 is greater than 0, positive. All right, and if we sketched it just from the information that we have there, we have a couple of things. And the thing that I circled in green, that's just a point on the regular graph, right? Because this is g of -5 equals 4. So that means the point on the original graph of -5, 4. All right, so let's start there. Let's see, -5, 4, be over to the left more than the right. All right. So we got that. We know that it's concave up, and we know that at -5, 4, the derivative is equal to 0. So here's just a sketch, concave up. Actually, I should do that in yellow. And we know that -5 is a critical point, right? And if you evaluated -5, or actually you don't even have to do that because they give it to you. So we know it's a critical point because the first derivative is equal to 0. So they gave us the point that goes with -5 on the regular graph, which is 5, 4. And we also know that at -5, what color did I use for that? Yeah, pink. That the derivative at that point is equal to 0. Since it's concave up, we can say that that point, not only is it a critical point, but it's also a local min. Because if it's concave up, it must be a min. Very good.
Can you repeat how you got 4 as a y value, please?
Yeah, I just got it from this right here.
Oh, that's right. My bad.
That's okay. This, and I was thinking the same thing. And I'm like trying to go back to a function. I'm like, no, they're giving me points, not a function. So yeah. I mean, you don't have to figure it out. They're giving you everything you need there. Okay, here's another example. Figure shows a population growing towards a limiting population, kind of like the coronavirus, right? I don't know where this L came from. Oh, sorry, they're naming it L. Like instead of f of x or whatever, right? Identify the inflection point and determine the significance of the inflection point to the population. So basically what's happening is this. So here, the rate the population type this. Maybe I will. Yeah, I think that would be fine. So we could say that the rate the population is increasing, that's the derivative, right? Is increasing, right? The rate is increasing. And that is what I just drew in blue. Then what happens is it increases the fastest at the inflection point. And then finally, oops. Oh, so let's do this again. Finally, then the population increases slower every day after that. Okay, so we've got Okay, so here's what I mean, right? See how the slope at a point increases until it reaches the inflection point where it's increasing the fastest. Right, it's the highest slope that you can get on that. And then after that, it slows down. Until it levels off, like you guys know. What is happening right now with the coronavirus, right? Okay,
Can you go back up for 1 second, please?
mm-hmm.
I just wanted to draw what you wrote.
So for a question like this, do we just estimate, like roughly right about where it's?
Yeah, actually, it does ask you to do it, right? Yeah, I forgot that part, sorry. Yeah, so just roughly, you could say that this point is about 27, and then for the X value, and maybe 175. And there's a margin of error in there, obviously.
Okay, thank you.
Identify the inflection.
Thank you.
Okay. Okay, so we're gonna, in this example, use the first derivative to find all critical points and use the second derivative to find all inflection points. And you can find an inflection point by setting the second derivative equal to 0 and solving. Okay, so let's color code this. Let's see, we're gonna go use the first derivative to find critical points. So the derivative of that would just be using the power rule, 3x squared minus 3. Set that equal to 0 and solve. You can factor out the 3 real quick. And then use the difference of squares pattern to further factor it. And get rid of the 3 and just set x plus 1 equal to 0 and x minus 1 equal to 0. All right, now let's do the second derivative. Let me give you a minute. Okay, so x is -1 is one critical point, x is +1 is another one. Let's just, those are critical points. Let's evaluate. So if we have f of -1, we'll put -1 into the original equation, we'll get 12. And we have f of 1, and we'll get 8. So notice that on Desmos, I just graphed this, and then top, usually if you touch a max or a min, even if it's local, it'll come up on Desmos. If it's not, when you touch here, right, you might have to guess, and you have to hold the cursor down to get it to show you a point. Okay, so this would give us those 2 points. And then the second derivative test to find all the inflection points, we're just going to find the second derivative, set it equal to 0. So the second derivative is, let's see, 6x, right? Because we're taking the first derivative and using the power rule. And then if you take the derivative of a constant, it's just 0. So it goes away. So then we just set 6x equal to 0 and solve. So you get your inflection point at 0. And there it is on the graph. And then once you, it said whenever they ask you to use a graph, definitely use Desmos or your graphing calculator. I'm coming around to Desmos, actually. I sort of fought it in high school And all my calculators in high school, my TI-84s used to disappear, like kids would take them home with them. Because we had a class set. I started out with like 35 and end the year with like 12 calculators left, just because people didn't return them. But my fellow teachers were saying, you're missing out. You forget about the graphing calculator. Desmos is super popular. And since you guys are taking your test online, there's nothing wrong with you using that as a calculator. All right. So what else is it? Use the graph to identify each critical point as a local max and local min. Well, it's obvious, right? We can just look at this and say that this is a local max and this is your local min. Guys, can you turn your cameras back on, please? That helps me figure out if you're still writing or if you need help or whatever. Thank you.
Mine affects the connection. Is it okay if I
Okay.
keep mine off?
Yeah, that's fine, Tom.
Sorry.
That's all right. Okay, looks like everybody's ready. Daphne, you good? Okay. Okay, now this is the same thing that we were doing, right? We're going to find the first and second derivative and the critical points and find inflection points. And then I'm going to ask you a couple other questions. This is a little different than what we just did because I'm asking you about a specific interval. I'm asking you for I'm only interested in the interval from negative 0.5 to positive 3. So it makes it slightly different. So if we find the first and the second derivative, the first derivative is just going to be 6x squared, right? Yeah, 6x squared minus 18x plus 12. And then the second derivative is just going to be 12x to the first minus 18. Okay. Next step is to find the critical points of f. So how do you find the critical points of f? What do? Use the first derivative or the second derivative?
First.
First, yeah, thank you. So we're going to put 6x squared minus 18x plus 12 equal to 0 and just factor the crap out of it, right? So we're going to pull the GCF out. And then factor further. So you have, what is it, x minus 1, x minus 2. Then you're going to set each of those equal to 0 and solve for the critical point. How do we find the inflection point?
By finding the second derivative.
Yeah, we
So-
already found the second derivative, and then what? Jadel?
Setting the second derivative to 0.
Got it. All right, so we're going to say 12x minus 18 equals 0. And then solve for x, so you just get, what, 12x. X is 18 over 12, which can be reduced to 3 over 2. I might as well just say that's 1.5. All right. So now we're going to, this is the same problem. Evaluate F at its critical points and at the endpoints of the given interval. So the endpoints are given up here. All right, but first let's evaluate it on the critical points. All right, so if we know that the critical points are 1 and 2, right? From setting the first derivative equal to 0 and solving. So if you put a 1 into the equation, the original function, you're going to get a 6 out. That gives us a point on the graph. And if I put our other critical point of 2 in, I'm going to get a 5 out. For the endpoints, you're just going to evaluate it at 0.5. You do that, you'll get negative 7.5. And if you evaluate it on the other endpoint, positive 3, you'll get a positive 10.
Shouldn't 0.5 be negative?
Oh, yes, thank you. Thank you for catching that stuff. I appreciate it. Okay. So now we found the inflection point is when x is equal to 1.5. Also, what did I do? That's blue. I put that into the function, and I'm going to get 5.5. So this is what I mean by evaluate at its critical points and the endpoints. So what you have here is a series of points available for you. So here is, here are the points, right? Here's 1, 6 right here. That's a local max. 2, 5 is right here on the graph. And what else do we have that's actually shown on the graph? Negative 0.5, negative 7.5 would probably be somewhere down here. Let me put that in that same color. And 3 and 10 would probably be up here, right? So you can just use all your points and graph them to get a nice graph, or use Desmos to get a nice graph. So let's label some of this stuff. So we've got a local max and a local min. Now, since we're evaluating this on a specific interval, we also have a global min. Let's pretend it's down here. And also a global max. So if you're doing intervals, you're going to have a global min and a global max for sure. And then one other thing I didn't mention, and it doesn't really show up here either very nicely. What happens since it's going from, it doesn't show greatly in this graph, but when it's going from concave down to concave up, what's going to be in the middle of those 2 points? What's it called?
The inflection point.
Yep. So I'm not going to ask you to draw a graph for me, but there will be a question on your test that will ask you to identify the correct graph. All right, any questions so far? I'm trying to get it all in. I hope you guys don't feel like I'm rushing, but I want you to see as many examples as I can possibly do until 4:15. All right. Sorry, I labeled this wrong. Okay. So here it says a biologist found that the number of Drosophila fruit flies, N of T, assumes the following growth pattern if the food source is limited. This should have been over here. How many fruit flies were there? This is not a trick question. Think about it. This is, I swear, it's algebra 2. How many fruit flies were there in the beginning?
$500.
No, but I understand why you're saying that, because you're thinking 500 is the initial value, right, Joey?
Yeah.
Yeah, it's a very educated guess, actually. But if you look at it, what does T stand for? Do you think? We're talking about growth pattern. Over what?
Time, I'm guessing in
Yeah,
years.
time. So before they start the study, where's time? How much time has passed before they start? They're measuring growth pattern from a certain time, right? So all we're looking for here is N of 0. Right? Time, this is the beginning, right? Time is equal to 0. So if you do N of 0, you're going to get 500 divided by 1 plus 38 e to the negative 0.4 times 0. If you put that in your calculator, you're not going to get 500. You're going to get 12 something. What was it? 12.82. Now, here's a wily trick, though. What are you going to answer the question if I'm asking you to the nearest fly? What's the answer going to be?
13.
Yeah, 13. Okay, here's another example. Totally different example too, completely different. It says, if R is the percent maximum response, you have to pay attention to what they want, what they're saying R is, right? And what X is. So R is percent of maximum response. And notice this word percent. So I'm going to put up here to remind myself that that percent is already in the problem. So if you say the first question is what dose, right? You're looking for an X value here, corresponds to a response time of 50%. Well, remember, this is response. So what you're looking for is 50%. So you want, when the Y value is 50, you want the X value, right? The X value is the dose. So if you know the Y value, how can you find the X value?
Set the equation equal to y.
We are going to set the equation equal to something. And remember that R, right? This side on the left is the percent response. And they're asking us, well, what's the X value when the response is 50%, right? So we're going to stick 50 in for R, since R is the percent maximum response, right? So 50 is equal to that equation. And now we're just going to solve that equation. So let's see. First thing I'm going to do is multiply both sides by the denominator. I have 50 times the denominator, 1 plus 100e negative 0.1x equals 100, right? Because if I multiply it by the denominator, it's going to cancel on the right side altogether and leave you with just 100. And then from there, let's see, I can divide both sides by 50. So I get 1 plus 100 e 0.1x is equal to 2. 100 divided by 50 is 2. Then I can subtract 1 to get 100 e 0.1x is equal to 1. And then I can divide both sides by 100. And then how do you take care of exponential and e as you use the natural log? So I'm just going to take the natural log of both sides. Remember, natural log has base e. So what happens when you take the natural log of a base e is that the natural log and the e go away.
Professor,
Yeah,
how come the 0.1 changed from negative to not negative? The e to the 0.1x.
you did not, sorry. Thank you for pointing that out. I really do appreciate it. You guys are very respectful about it too. Thank you. Okay, so what we have here is negative 0.1x is equal to the natural log of 0.01. And then you will have divide both sides by negative 0.1 and you get x is equal to the natural log of 0.01 divided by negative 0.1. And you get 46.05. And then this, of course, is the x value, right? So we're talking about what's it? milligrams. So we could say that this point right here would be 46. Okay, now, oh, wait, you guys are dragging, I'll wait. Everybody okay? Okay. All right, now here it says for this drug, a minimum desired response is 20% and the maximum safe response is 70%. What's the range of doses? Which range of doses is both safe and effective for this drug? Well, first, let's look back at this graph for a minute. So what do we have? 20% and 70%. So let's say 20% would be around here and 70% would be around here. So what we're looking for is what are the X values in that range, right? Given the Y values. Well, just like we did here, we found the X value by putting in the Y value. That's how we can find the range. So we would just do $20 is equal to 100 over 1 plus e to the negative 0.1 x. And you would get the same way that I did the above problem, you'd get 32.2. You would also do it for 70. And you would get x is equal to 54.52. So you could say the range is in between 32.2 and 54.52. Okay, now we're doing surge functions. All right, so first of all, a surge function is different from a logistic function. The graph on a surge function looks something like where it slowly comes up, peaks, and then slowly goes down. This is where the drug concentration kind of problems come in. Let's see, how long does it take? I wanted to see if I could type something in for you here. Let's see. All right, I'll just do this. So what we're going to do to answer that first question is find where the derivative is 0. And you can kind of see on this graph, it would be up there, right? And also, if you read the graph, that's where it's going to reach the peak concentration. So let's see, let's find the derivative. We're going to use the product rule. So we've got, oops. FG product rule says you go F prime G plus FG prime. Okay, but the first thing I'm going to do is recognize that this is a constant. So I'm going to take the 6.5 out of the question. Otherwise, I'm going to have to be multiplying it by steps. So I'm going to say that C prime T, or the derivative of that function, is going to, no matter what it is, you're going to multiply it by 6.5 when you're done. It'll save us a lot of trouble. All right, so now I'm going to do the product rule where this is because it's a constant multiple. Okay, so my F is going to be my T, and my E to the negative 0.4 T is going to be my G, just so you guys can follow. All right, so F prime is going to be 1, right? Because T to the first power, so we've got 1 times G, we're just going to leave G alone, so that's E to the negative 0.4 T, plus, we're going to take or I'm going to use this rule. Remember, let's see, the derivative of e to the kt power equals ke to the kt power. So that's all I'm using right here for the second part here. So I'm going to get negative 0.4. Oops, let me write that. Because the k in this is 0.4. So 0.4. And that's a negative. Negative 0.4 t e to the negative 0.4 t power. So I'm just using that rule up there. All right, now I guess I could simplify this by, well, maybe not. Yeah, I could simplify this a little bit. So this is really e negative 0.4 t minus 0.4 t e to the negative 0.4 t power. And then I could even simplify it more by taking the GCF of that out, right? So here's the 6.5. And then I could take this GCF, which is e to the negative 0.4 t power, and factor it out to get 1 minus 0.4 t. So remember, we're trying to figure out where is the derivative equal to 0. Well, so now I would set this whole thing equal to 0, right? And solve it. Well, both these things are going to go away, the 6.5 and the e to the negative 0.4 t, because all we have to do is divide both sides by those. So you would just be left with the part with your, no, sorry, the 6.5 would go away. So we have 0 equals e to the negative 0.4 t 1 minus 0.4 t. So now if you multiply both sides of the equation, or sorry, divide both sides of the equation by the e, that'll go away too, and you'll just end up with 0 equals 1 minus 0.4 t. Solve that for 0, and you get negative 0.4 t equals negative 1, or t is equal to 2.5 hours. So to answer this other question that says, what is the peak concentration of the drug? We're just going to do the original function C of 2.5 hours to get 5.98 nanograms per milliliter. And let's look back up at the top here. Do you guys need a minute? All right, looks like you're right. Let me give you a sec. Okay, so looking back at the top here, we have to look back at what this equation means, right? So T is time, C is concentration. So this next question is saying, what is the concentration of the drug after 1.5 hours? So how would you answer that question? It's not hard.
You just plug 1.5 into the function.
Absolutely. You'd find C of 1.5. So you're just plugging it into the equation. 6.5, the original equation, 6.5, 1.5, e to the negative 4, negative 0.45. (1.5). And you would get 5.35 nanograms per milliliter. And do the same thing for 5, right? You just find C of 5. And you would get 4.4 nanograms per milliliter. Now, in this question, this next question that I'm going to ask you, you should use Desmos to answer the question. So I think I copied my Desmos graph. Everybody set to go on? Okay. So here's the graph, the original graph function. If the minimum effective concentration is 2.5, when should the next dose be administered? All right. So what we're going to do is, here's the original function, just since it's far away, equals 6.5 e to the negative 0.4 t. So what we want to know is what is when the concentration in this case, and it's a coincidence, by the way, that they're using 2.5 and the answer to this other question was 2.5. It's totally a coincidence. Don't think that they're related. They are not. So they want to know what's the constant, when the concentration is 2.5, what is the time, right? So instead of doing that, and you guys can solve that because we just did it before, but instead of doing that, they're interested here. So this is 2.5, and this is concentration over here. Oops. Oh, I think I must have graphed the wrong one. Shoot. This is kind of what the graph would look like. And this is not the right value right here, sorry. This would look like, let's say, see, this is, that value up there is more like 5, right? Because you can see the 0 and the 10, so that's not a correct, that must have been another point I was trying to get at, which is over here. So if this is about 5, 2.5 would be somewhere around here. Okay. So that's a 2.5 nanogram per milliliter. All right, and what we found out is when we click on this point on Desmos right here, if you click on that point, you're going to get 2.5 and 0.45 right there. And remember, the x-axis is time, right? So 0.45 of an hour has passed, right? And so that means that, it takes half an hour or whatever for this to be at acceptable levels, right? So what you need to find after that in order to answer this question is the point over here, because that has a time associated with it also, right? Now notice that this level up here is an acceptable level of concentration, right? The minute it drops below that level, it's not acceptable anymore. And that's when the next dose should be delivered, right? So what we would need to know here is the X value at that point. Well, in Desmos, if you click on it, you would get this point, 7.36. Remember, the X values is time, and that would also go with the concentration level of 2.5. And we're talking time on the x-axis, guys. So we went from a half an hour to 7 and almost another half an hour. So about how many hours should you give the next dose? So if you look at the distance from here to here, so if you do 7.36 minus 0.45, you get approximately what, 6.9. So you could say about 7 hours later. Remember what the graph is giving you. It's giving you the concentration level in a patient, right, after taking medication. So it makes sense that here it takes it some time to get up to the minimum level, right, which is 2.5 in the system. And then once it travels here, it's declining in concentration. They say they don't want it to go below 2.5. So where's the point that it does go below? It would be right there, and that would represent 7.36 hours later. So you take the two difference of those, and you'll get when the next dose should be administered. All right, so that's chapter 4, or not chapter 4. That's 5.1 and 5.2. And this last section is quick for 5.3. So I understand if you guys have another class and you need to go at 4:15, but I'm going to keep going and I'll post the video. Guys, I just want you to have as many examples as possible to look through. Okay, so here is 5.3. Following table gives world oil consumption in billions, give the bounds of the true quantity of oil consumption. So what we're looking for here is the left and right hand sum. And the left-hand sum would be these values. And the right-hand sum would be these values. So the left-hand sum would be, for example, would be 20.8 times 5, right? Plus 23.2 times 5. Plus 25.5 times 5, again, 27.9, and so on, right? You get 640.5 billion. Notice it is in billions. Do the right-hand sum, it's the same idea. So you, instead, this time you're going to start with 23.2. And here you get 696.5 billion. So how can we get a better answer than that? You guys remember?
Take the average.
Yeah, thank you. So if you take 640.5 plus 696.5 and divide it by 2, you'll get an even better answer.
So for the left-hand sum, it's always going to be the 5 values minus the, or excluding the largest value for like the
Correct.
bottom portion. And
Yes,
then
that's correct.
right hand, it's just the same, but minus the smallest value.
Yep, Tom, that's right.
Okay.
All right, let me move on. So the rectangles here are approximating the integral from 0 to 9 of some function called g of x. First question, do the rectangles represent a left or right sum? Well, because the rectangles touch the right side, it's a right sum. So what do you guys think? Is this an upper or a lower estimate?
An upper.
Tell me why. So the total area is more than what's under the graph, right? So it's kind of, it's like an overestimate, right? Because the rectangles go beyond the actual graph. Who could tell me the value of n? How many intervals do we have? 3, yeah, Jadel, good. And what is the change in x?
Would it be 5?
It would. Can you tell us all why, please?
What?
Can you tell us all why, please?
Oh, because you would divide the 15 by the 3.
Okay. Okay, I'm going to skip over number 12. I'll go back and fill those notes in for you, but we kind of already did it. Left and right hand. I'll do that just so you guys can go. So example 12 is find the area between 0 and 8. This is where you're going to have to use your calculator. You're going to use x instead of t. And x here too in your calculator. And again, the keystrokes on a, I think on Desmos it's crazy easy because you just look for that function. But if you're using a graphing calculator, you want to go to the math option. And then scroll down to where it says FN int, short for integral. On my calculator, it's option 9, but it could be something different on yours. So if they're asking you to find an area and they're giving you the function, that's when we get to use the calculator. Now here's a cool use for Desmos. So here it says find the area enclosed by 2 different functions, right? So first thing I would do is graph it and say, what are we talking about here? So we're talking about the shaded area there, right? We want the area enclosed by those two. So we could do the integral of 2x minus 2x squared dx, right? We could just put it right in our calculator, but there's a specific interval they're interested in, right? So they're interested in from here to here, right? So on your graph, you know that that point is 1, 2, and you know this point is 0, 0. So that means you're going on the x value, right? Let's use a different color. So that's where you're going to get your bounds, right? From 0 to 1 is what you're interested in. And then you could just use a calculator. You would get 0.33. So notice they don't give you bounds here, right? So if you graph that on Desmos, though, you would see the area that is enclosed goes from x is equal to 0 to x is equal to 1. You could have algebraically done it too to find the intersections. Just set each equation equal to each other and solve for x. That would work also. Much quicker though to just use the calculator, find the intersections of the two graphs. So, and you can do that on TI-83 also. All right, one more. Guys, you've been so patient. Everybody done with this one? All right. This one is easy. You guys remember this. So use the figure to find the following values. So we're looking for the area from A to B. What do you guys think for the first one?
13.
Yes, 13. They give it to you right here, right? So this is 13. What about the area from B to C? What's that?
2.
Yep, there it is right there, right? So if we want the area from A to C, what would we do?
Would you subtract 2 from 13?
Oh, you know what yes, you do. Sorry, this should be a -2. Sorry, since it's below the x-axis. Okay, and they're in this diagram, they're saying the area is 2, but since it's below the x-axis, it's got to be negative. So yeah, you're right that to find the area of the whole thing, which includes the positive part and the negative part, you're going to take 13 and subtract 2 or add -2 is probably a better way to see it. So you'll get the answer that the whole thing is equal to 11. But this is the kind of question where I said before, if I'm asking you for the total area, then in this case, you're really going to use the absolute value of that. So it would be the absolute value of 13 plus, let's say, plus -2. So in this case, you'd get 13 plus 2 or 15. And that's the last example. Thank you guys for staying. I'm sorry I kept you a little bit longer, but I just wanted to get as many examples in as possible and let the video run too so people could come back and watch it. You guys have any questions for me?
You're gonna post this on Moodle, right?
Yes, I'm going to post it on Moodle. I'm going to print it out and post it on Moodle and also post the video of this on my YouTube channel,
Okay.
like I
thank you.
do every week. Yeah. All right, guys, you are free to go. Have a great
Thank you.
day.
Thank
Have a
you.
good one.
Bye,
Thank
guys.
you.
Sure.
I have a Wiley question.
Go for it, Jadelle.
Can I, 1 second. it's a homework question. So if anybody else has a question, I can go on mute while I find it.
Go ahead. You're up first, Jadelle. Actually, you know what? I need to end this recording. Otherwise, all of everything that we say is gonna, so let me do this. I'm gonna end this recording and I'll come back to the meeting for you guys, okay?
Okay.
Okay, so just stay here. I'll be right back.